So that ones and zeros should be converted to a voltage signal. Okay. For example, 1 can be mapped to 5 voltage, 0 can be mapped to 0 voltage. Likewise, we can map that value 1 and 0 to particular voltage level. So that process is called the line coding. Okay, it is okay. So I will share my screen. Can you guys see my screen?
Yes, sir.
Okay. I think you have requested to derive the spectrum of sinc function. Okay, sinc function and sinc square function. So first I will do it. Okay. So I think to derive the sinc square function, okay, sinc square function, it is somewhat the process is too long. Okay, because our calculation we have to do some integration. That integration will be too long. We have to integrate by parts and come to the answer. Okay, we have to come to the answer by using integration by parts and many things. Okay, so the process is too long, but it is not difficult. Anyway, first I will start the sinc function. Okay, sinc function. Okay, because this is somewhat easy. Okay, there. Okay, so first of all, I think you already know the rectangular pulse, no? Rectangular pulse. Okay, rectangular pulse. So this is the basic pulse type we are using in digital communication systems. Okay, like this. Okay, so write it like this. So I already told you that we have in digital communication, in the digital domain, we represent our information using 1 and 0 like this. Okay, so this 1 and 0 should be mapped to voltage level somehow. Okay, otherwise we can't process it. Okay, so we can, okay, we can just map here 5 volt, here 0 volt, 5 volt. Likewise we can map. Okay, so so say that here we for 0 we assign minus 5 volt. Likewise. Okay, so here it is 5 volt minus 5 volt. Likewise. Okay, so you can see that then we can have a pulse train. Okay, so this is a pulse train. Okay, so for 1 we have 5 volt. Okay, and 0 we have minus 5 volt. 1 again has 5 volt. Likewise we will get this kind of a pattern, no? So this is a pulse train because pulses are there. Okay, so so in digital communication we have to use this pulse train everywhere. Okay, so this is the source. No, this is our source. Actually, this is our information source. Okay, so the one thing is that so actually this process we call line coding. Okay, that is why I asking you that you have learned about line coding. You will learn this about in future. Okay, but here it is okay to have idea. Okay, otherwise we can't move on. Okay, so this is called line coding and we call this NR reset line. Okay, NRZ means non-return to zero. That means here within pulse width, this is within one. So this is the information one and this is information zero. Okay, for information one duration, okay, for this duration, for one pulse duration, it's not come to zero. Okay, it has some voltage value here, plus value, and for zero we have -5 minus value like this. So it is not come to zero at within this period. Okay, within this pulse period, it is not reached to zero. That is why it is called non-return to zero. Okay, but some line coding methods we have, we for synchronization process, synchronization issue, sometimes we within pulse we uh, return this pulse to zero like this. Okay, so here one pulse, one information bit, one bit is representing using is represented using two pulses. Okay, so this is called return to zero. Okay, and normally this is the basic line coding method, non-return to zero. Okay, this is additional information. Okay, just get the idea. Okay, no need to get thorough with this. Okay, so anyway, okay. So what I want to tell you is that, okay, so you can see that in digital communication, we are using pulse train, most probably pulse train. Okay, so pulse train is formed with pulse, no? So collection of pulse, collection of pulse, collection of pulse, okay, will made a pulse train. Okay, okay. So collection of pulse will make a pulse train. Okay, so that is very clear, no? Okay, so study about this pulse is also very important in communication. Okay, so this is rectangular pulse, no? Because this is in rectangular form. Okay, so we call this rectangular pulse. Okay, in signal and system you have learned these things. Okay, so I hope you maybe remember somewhat. Okay, so anyway, okay, so this is rectangular pulse. Okay, so here it's t. Okay, so I will have a symmetrical pulse. Okay, because for analyzing easiness. Okay, so here this is I will take this is as minus tau and this is plus tau. So what is this value? It is 2 tau, no? 2 tau. So that is the pulse duration, no? That is the pulse duration. Okay, pulse duration, and we called it pulse width. Okay, pulse width. Okay, so I think you can remember that we can denote this function, this signal as this one pulse signal as rectangle t plus tau. Okay, so tau is the pulse width. Okay, tau is the pulse width. Okay, pulse width. Okay, tau is the pulse width, and if here have some value, that is the amplitude, the level of the pulse. Okay, level of the pulse. So here it is the pulse width is 2 tau, so this should be 2 tau. In this case, this should be 2 tau. Okay, so because 2 tau is the pulse width. Okay? So this not in this notation we can represent this pulse. Okay, we represent this pulse. Okay, so I think now you have start to study about baseband transmission, no? Baseband transmission. Hope you have already started this. Did we start this baseband transmission? Can anyone tell? Yeah, you have learned, no? Yeah, thank you. So you have already learned about the baseband transmission. So what is baseband transmission? So can anyone tell? You can talk, okay? No need to type. Just tell me what is baseband transmission. It is better talk with me, okay? Then you can improve your communication skills also. Okay, it is another advantage. Okay. Yeah, transfer of digital pulse. Yeah, we can say that. We can say actually in baseband transmission, we are sending pulse. Okay, we are sending pulse. Okay, actually pulse are sending in analog baseband transmission. Okay, sorry, digital baseband transmission. Okay, so pulse are sending in digital baseband transmission. So I already told you that our information 1 and 0, okay, map this bit stream. This is a bit stream, okay, and using line coding techniques, okay, to process this the 1 and 0, that is the binary value, no, it is a binary sequence. Okay, so this is a binary sequence, only a binary sequence. Okay, so this binary sequence should be in voltage form, otherwise we can't process it through electronically, no. This should be electrical form. Okay, otherwise we can't process. Okay, 1 and 0 we can't process. 1 and 0, if we give 1, our electronics component cannot identify it, 1 and 0. But if you send some voltage pulse or current pulse, okay, it can detect by any electronic component, no. So to process this information electronically, or implement some electronic circuits, okay, to represent this kind of digital signal, we have to convert this binary sequence into voltage levels, okay, voltage pulse, like this. Okay, so this is actually line coding, I already told you. Okay, so you can see that this is our information signal, no, is it okay? So this pulse train is our information signal. Okay, information signal, is it okay? This is information signal, no. So can you remember that I have told you several times, normally we refer baseband signal for our information signal, no, or modulating signal, information signal or modulating signal. Okay, information signal or modulating signal. Okay. So this is baseband signal. Okay, so that is the information signal or modulating signal. No, baseband signal means information signal. So you can see that this is the information signal. Okay, and if this information signal is directly sent, so this information signal, that means it's a baseband signal, no. If we describe it further, it is a digital baseband signal. So only two levels are there, two voltage levels are there, maybe 5 volt and 0. So limited voltage levels are there. So it is a digital signal. Okay, only few levels are there. So that is a digital signals. Okay, so this is a digital baseband signal. Okay, so if you transmit this signal directly, we call it digital baseband transmission. Okay, correct. But if you talk to a microphone, okay, so it will generate some analog signal like this, no, like this, analog continuous time signal like this. This is our voice signal. Okay, voice signal generated by a microphone, And also this is also a baseband signal. Okay, this is a baseband signal. So if you directly send this signal, okay, that's also a baseband transmission. Okay, that's also a baseband transmission. Okay, so can't we send this signal directly? Can anyone tell? Can't we send this signal directly? Can we send this signal directly or not? Okay, this we got a message. No, actually we can send this signal directly. Okay, you are correct. Okay, noise and attenuation will be there. Okay, noise and attenuation will be there. Okay, but we can send it. No, yeah, you are correct. Okay, noise and attenuation will be there when you are sending the signal. Okay, noise will add to it. Okay, and also the signal will be attenuated. Both things happen, but we can send that. Okay, we can send, but we can't send it through wireless channel. Okay, we can't send it to wireless channel. Why we can't send it through wireless channel? We can't generate RF signal, no? So we have to make very big antenna. So it is not practical. So practically we can't send this baseband signal, this analog baseband signal in a wireless channel, but we can send it to a guided media, no? Coaxial cable or twisted pair cable using a coaxial cable. Okay, coaxial cable or twisted pair cable. We can send it. No, actually we have done it when our village have some festival. Okay, we are using our microphone here, and this microphone is connected using wire to a loudspeaker. Okay, and this loudspeaker may be in a tree or somewhere. Okay, so when you are singing song here, speaking something, you can hear it from here, no, from this loudspeaker. So here it is a baseband transmission. Okay, so here also a baseband transmission. No, did you do any modulation here? No, just you will use amplifier. Okay, you will sometime use amplifier here. The amplifier will not do any modulation. Okay, so this is you can control some. So here some filters also there. Okay, so you can adjust some noise level, and you can adjust the noise and the signal levels. Okay, so this amplifier will do that thing. Okay, but here there is no any modulation. Okay, so you directly send this signal. Okay, so here it is a baseband transmission, but it is analog transmission. We can do it. Okay, no issue. Okay, but nowadays we mostly use digital transmission. Okay, okay. So so you can see that in baseband transmission also, we are seen in digital baseband transmission. In digital baseband transmission, we are using this pulse directly. Okay, so can this pulse sent through a wireless channel? Can this pulse sent through a wireless channel? We can't. No, we can't send. Okay, we have to convert this to RF signal, and we can send it. Okay, we can't directly send this pulse through wireless channel. That is impossible. Okay, this is impossible. Okay, but we can send this pulse through a cable. Okay, coaxial cable, twisted pair cable. Okay, through twisted pair cable or coaxial cable, we can send this pulse. Okay, so normally digital baseband transmission is okay for line. If the transmission media is a via, okay, guided transmission media, we can use this baseband transmission, digital baseband transmission. Otherwise, we can't do. But still, we are doing this digital baseband transmission. Okay. So, so, so for baseband transmission. So, if you want to understand this baseband transmission also very clearly, you have to learn about this pulse. Okay, rectangular pulse. Okay. So, I think already you know how to find the spectrum of this rectangular pulse. Okay. I think you already know it. Okay. So I will write my pulse here again. Okay. So if we have a pulse like this, okay, it is from minus tau to plus tau, say. So the pulse width is 2 tau. Okay. So let's take as pulse the value is A or B something. A. Okay. So you are asked to find the spectrum of this pulse. Okay. So how can we find it? So to find the spectrum, you have to definitely find the Fourier transform. No? So I think very easily you can find the Fourier transform here. Okay. So Fourier transform is given like this. Okay. If we have a time domain signal, if we get the Fourier transform x omega, we can evaluate it through this integral minus infinity to plus infinity xt, our time domain signal, e to the power j omega t dt. Okay, so this is our Fourier transform pair. Actually, there are many different method. Okay, very different method. Sometimes this denote as j omega. Okay, and also with this is with f. Okay, but usually I use this method. Okay, because it is easy. In exam also you can use any form you wish. Okay. Okay, so if you evaluate this integration, okay, so it is very easy. You can see that. So xt is here is a, okay, xt here is a. So if I integrate it minus infinity to plus infinity a, so it is not minus infinity to plus infinity. It is from minus tau to plus tau. No? This up to here it is 0, and from here to up to infinity it is also 0. So the pulse limit is minus tau to plus tau. Okay, a. Okay, and e to the power minus j omega t dt. So you can easily do this integration. So integration is a e to the power minus j omega t divided by minus j omega. This is the integrated value. Okay, so you have upper limit minus tau plus tau. Okay, so if you get, if you apply these limits, okay, so you will have, I will get this j omega, a j omega out minus a j omega out. So this is the upper limit. So we have e to the power minus j omega tau minus e to the power. So here minus minus is, it will be plus. Okay, j omega tau. Okay. So if I do any mistake, please let me know. Okay. Otherwise, I continue it. Okay. So if I am doing any mistake, if you can see this minus change, plus change, you can tell me. Okay. So here minus, say I can divide, I can multiply it by minus minus. So I will get this one here. Okay. So I will write this a j omega to the power j omega tau minus e to the power minus j omega tau. Okay, so you know that this is using the Euler formula. We can convert this to sine and cosine value. So you know that e to the power j theta. Okay, e to the power j theta is equal to cos theta plus j sine theta. Okay, e to the power minus j theta is equal to cos theta minus j sine theta. Okay, so if you add, if you subtract this 2 from 1, okay, you will have e j theta minus e minus j theta as 2j sine theta. Okay, so for this one we can apply this. Okay, so we have again a j omega, okay, 2j 2j sine j omega tau, no? Okay, sorry, this j is not here. Okay, correct, because only theta is there. Okay, this is sine theta, theta is only there, so it is sine omega tau. Okay, so this can be, this is the answer, no? So we can form this like this. Okay, so you can see that we can form this as, so you can see that j and j cancel out, so we have 2a. Okay, 2a, we can write this as sine omega tau by omega tau. Okay, so here omega is already there, but there is no tau value, so I put here tau. Okay, so this way we can write, no? Yeah, okay, so this is the answer. This is the spectrum of that signal, this signal. Okay, spectrum of this signal. Okay, so if I write the spectrum, if I draw the spectrum, so how it like? Okay, so I think you can remember that. Okay, when you start to learn calculus, you learn these things. Can you remember in A level you have learned this? This is equal to 1 sine theta by theta. If the theta is limited to 0, it is 1. Okay, so you have learned this identity, no? When you start to, when you first start the calculus, at the start of calculus, we learn this identity, no? Sine theta by theta is equal to 1. Okay, so so I'm going to write this spectrum. Okay, so here I'm going to write this spectrum. Okay, so here we have omega. Okay, so I'm going to write the spectrum of this xt. Okay, so it is in frequency domain, no? So I have to write it in omega. Okay, and this is x omega. Okay, Fourier transform of frequency spectrum of xt. Okay, so you can see that if omega is 0, omega is 0, this is 0 and this is 0, so sine 0, sine 0, that is 1, no? Sine 0, sine 0, that is 1 using this identity. Okay, when we are finding the limits, we in an advanced level, when you are finding the limits, can you remember that we have used this identity several times, no? Sine theta by theta is equal to 1. Okay, I can't remember how it proof. Okay, I hope in advanced level we proof it, no? Now I can't remember how it come. Anyway, it is we can use it as a fact. Okay, non-fact. Okay, so you can see that at 0 it is 1. Okay, but here some value is there, 2a tau. Okay, so here we have 1 into 2a tau, that means 2a tau is here. Okay, and you can see that when you are, so sine wave is like this, you already know. Okay, so this is the sine wave. Okay, so you can see that when omega is increasing, sine value is increasing. Okay, but sine omega tau, omega is increasing, sine is increasing, but omega tau is there, no? It as a denominator. This is denominator, no? I can't remember. Okay, so as a denominator, we have omega tau, because now sine increasing, but omega tau is also increasing. Okay, but you can see that this increase is less than this increase. Okay, so total value will be plus. Okay, so when you are increasing omega, this value will be low, will be the sine omega tau by omega tau will be reduced, okay, like this. Okay. Okay. So you can see that here to here, here to here, and here to here, it is reducing, and at 5, okay, so here it is sine 5 tau, okay, 5 tau, sorry, at 5, okay, so here it will be 0, okay, so that means here it is omega tau, no, omega tau is equal to 5, okay, omega tau is equal to 5. Can you remember, can you understand that omega 5 is equal to omega tau is equal to 5, okay, so here we have, if omega tau is equal to 5, we can see that sine omega tau is equal to sine 5. Sine 5 is 0, no? So this omega tau is equal to 5. This value will be 0. This value will be 0. Okay. So what is the omega value at that time? The omega value is 5 by tau, no? Okay. So at 5 by tau, omega is at 5 by tau. Okay. This value will be 0. Okay, that means this has some value, so total value will be 0. So this total value will be 0. Okay, so here omega is at 5 by tau, it is 0. Okay, and here in minus side, same thing happen. Okay, so you can see that when again it is increasing. Okay, again it is increasing like this. Okay, from this side, because it is increasing from this side, but you can see that omega tau is increasing also. So that increase will not reach to here, no, up to here, because omega tau is continuously increasing. The denominator part is continuously increasing. Okay, so the total value will be discrete with omega. Okay, so we have the discrete decreasing signal or decaying signal, signal like this. Okay, like this. Okay, like this. Okay, correct? Hope you understand it. Okay, hope you understand it. Okay, so you can see that what is this 0 point, 0 crossing point? What is this 0 crossing point? 0 crossing point is 5, no? 5. Here another crossing point to 5. Okay, and this point also 0 crossing to 5. Sorry, 3, 5, 4, 5, and minus side also same, no? So here it is 2, 5 by tau. Here it is 3, 5 by tau. Here it is 4, 5 by tau. Likewise, no? And here it is also 2, 5 by tau. Here 4, 5 by tau. Sorry, 3, 5 by tau. Here 4, 5 by tau. Like this. It will be decaying, no? So you can see that it is decaying because sine theta by theta. Okay, so you can see that sine theta have one range like this. Okay, but theta is increasing, so total value will be decaying like this. Okay, so can you understand? So we have the spectrum like this. Is it okay? I will write it here again. Okay, so we have rectangular pulse. It is a time domain signal. Okay, time domain pulse xt. We have a. Okay, here it is minus tau plus tau. Okay, so we can represent this signal as rectangle A rectangle, A is the amplitude of T by the lower part is the pulse width. So here the pulse width is 2 tau, no, 2 tau. So we have 2 tau. Okay, so this is our signal. Okay, and if you get the Fourier transform, okay, we will have this in omega, and here it is capital X omega, Fourier spectrum, okay, of this signal. Okay, so it is like this, no, it is like this. Okay, so here it is 2a tau, okay, 2a tau, and here it is cross at 5 by tau. Okay, here also 5 by tau. Okay, now again it is increasing, and this it is decaying, no, because sine theta theta, so sine theta is has a one range, okay, limited range, but this theta is increasing, no, when you are go through this line this way. Okay, that means theta is increasing, so this total value will be decreased with theta. So this amplitude will be less than this one. Okay, and this amplitude will be less than this one, this amplitude will be less than this one. Likewise it is decaying. Okay, and here also it is decaying. Okay, so it is happen as a sine wave. Okay, no any special things. Okay, it is behave as a sine wave, but this point it is not as a sine wave, because we have a special identity that sine theta by theta, when theta is limiting to 0, it is 1. So here it is 1. Okay, so here it will be 1 here. Okay, so other things is same as sine wave, but this amplitude is decaying. Okay, this amplitude, this peak is decaying in every circle. Okay, so 0 cosine point is same as in sine wave. Here it is 2 5 by 2, this 3 5 by 2, like this. Okay, and here it is 2 5 by 2 minus. Okay, these are minus, and this is 3 5 by 2 minus. Okay, so this is the spectrum. Okay, so did you get this? Hope you get it. Okay, so so actually you asked to find the sync wave, sync function spectrum. Okay, but I didn't, still I not I didn't discuss about this. Okay, I am still discussing about the spectrum of this rectangular pulse. Okay, so this rectangular pulse we normally use in our baseband transmission, no? Okay, so the spectrum is like this. Okay, so spectrum is like this. So what is the conclusion you can get when you look at this spectrum? Okay, so you can see that you can note one thing. What is this? Spectrum goes to infinity, plus infinity, and also to minus infinity, no? Is it okay? So this spectrum is going to plus infinity and minus infinity. Okay. Okay. So always spectrum tell us the bandwidth, no? Bandwidth required bandwidth. Okay. So what is the required bandwidth should channel have to send this pulse? So what is the, okay, what is the bandwidth, okay, bandwidth of a channel, okay, transmission channel, okay, bandwidth of a channel should have, okay, should have to send this pulse. Okay, so can you answer this? What is the bandwidth requirement of a channel to send this signal, to send this pulse? This pulse. What is that? How much bandwidth you need? So can anyone tell? So look at this spectrum. Okay. So what is the bandwidth? What is the bandwidth? Bandwidth is from here to here, no? Correct? Okay. So we have to have infinite bandwidth, no? We have to have infinite bandwidth. Infinite bandwidth. Okay. So is it okay for you? So it means that we can't send this pulse, no? Practically, we can't send this pulse without distortion. So I think you have learned about the distortion and distortionless transmission also. Okay, distortion and distortionless transmission also. Okay, so here it is a distorted transmission, no? If you try to send this kind of pulse through a wire, you can't send this. But practically you think, no, it is not happening, okay? Because if we have a battery here, okay, the same question already also I have when I'm learning, okay? If we have, and if this is a bulb, okay? If you switch this on and off, okay? So you on this for some time like this and off, and on this off, on this off. So this bulb also on, off, on, off, okay? So at once you can think that within wire we can send this pulse, no? Doesn't this come to your mind? Okay. So this is the first thing come to our minds, no? Using a wire, we normally send pulse. But this say that we can't send pulse through wire because this wire doesn't have infinite bandwidth, no? Okay. So what is the, how can you interpret this? Okay. So you can interpret this as, okay, actually for very low speed transmission, okay, we can send this pulse, no issue, okay, like this. Sometime it is okay, we can send, okay, practically we can send, okay, but the distance should be very low, okay, and the speed also very low, okay. If the distance is very low, okay, distance is very low, and speed also, the pulse rate is very low, speed, okay, very low, that means pulse rate. So I have already told you that if you want to increase the data rate, you have to reduce this pulse width, no? Can you remember that we have already discussed these things, okay? And all these related with this spectrum, okay? I will tell that. Okay, so this is very interesting if you clearly understand this, okay? Okay, so for if you send in very high pulse, this is not happen actually, okay? So you will get some distorted pulse here, okay? But if you send in very speed pulse, okay, to some kind of distance, 200 meter, 300 meter, so you can't send it. Okay, so you can you remember that sometime in coaxial cable we have some limitation, no? Coaxial cable we have some limitation. Twisted pair also we have some limitation. We said that coaxial cable, I can't remember exact value, you can find it. Okay, coaxial cable can send signal about 200 meters. Okay, the twisted pair can send only 100 meters, so on. I can't remember the exact value. Okay, and here the data rate is about uh, as I can remember, it is about 64 Mbps, correct? Or 128 Mbps or something, no? Okay. So this is the maximum level we can send. Okay, and here for twisted pair also we have less data rate here. Okay, so if coaxial have, I can't remember the exact value. The if the cable have 200 Mbps megabit per second, this twisted pair can limit it to 100 or 70 or something, 70 Mbps or something. Okay, so you can see that in this cable also we can't do the communication as we wish. Okay, we can't achieve very high data rate. It is limit. We have, there is always limitation. Okay, actually that's limitation comes because of this spectrum. Okay, so this spectrum is infinite. So always infinite things will create limit in another domain. Okay, that is also practical in our life. No, this time, this is finite time. This time domain is finite, but it will create, okay, infinite in frequency domain. So one domain finite, okay, one domain finite, but other domain it is infinite. Okay, so we have to always use the middle point. Okay, madhyama pratipada. Okay, so one extreme will create limit in another domain. Okay, අපි එක පැත්තකට එක දෙයක් බර කරගත්තොත් තව පැත්තකින් එක ලිමිට් වෙනවා. හරි, එක පැත්තක් මේවා කරගත්තොත් මේක අනිත් පැත්තෙන් ලිමිට් වෙනවා. හරි, තේරුණාද? right, ඒක mathematics විදියටත් ප්‍රෝ කරන්න පුළුවන්. Okay, so this is very important feature. Okay, that is why I try to tell you that. Okay, so here you can see that here it is time limitation but infinite in frequency. So this infinite of frequency will again create limitation in data rate and distance. Okay, okay, so you can see that. Okay, you can see that if we send a pulse through a coaxial cable, at here we will have this kind of signal sometime. Okay, not this. Okay, so if we send the pulse here about some kilometer through a coaxial cable, we have this kind of pulse. Okay, so what's happened is there, again you know that here we have infinite number of frequency, no, with this pulse has infinite number of frequency here. Look at the spectrum. Okay, so when you send it to someone, some frequency will cancel and you have some frequency component will cancel and you have other frequency component here. So you can't get the exact rectangular shape. Okay, okay, so I think you understand it. Okay, so again I will try to tell you another thing here. Okay, so this is tau, no, this is tau. So say I have I have selected, okay, I have selected tau by tau. Okay, I will write it here again. So you guys understand what I am talking here? Okay. So basically, if I tell it again, what you should know is, okay, if we have a rectangular pulse, okay, from plus minus to minus tau, okay, we will have this kind of spectrum, okay, this kind of spectrum, okay, like this, okay, 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 and this will be 5 by tau, and this will be plus 5, minus 5 by tau, okay, and this will be 2 5 by tau like this, okay, 2 5 by tau like this, okay. So I think it is better to keep remember this, okay, because this property we always have to use, okay. Right. Uh, right, Mama. So I told, so I select another pulse like this, okay. So it is tau by 2 to plus tau by 2, okay. So what is the spectrum here, okay. So you can see that here 5 by 2 is there, okay, okay. So 5 by 2, 5 by tau by 2, that means 2 will be go up, no, it will be 2 5 by 2. So for this green color signal, my spectrum will look like this, correct, like this. So here, so here, this is my red one, okay, and this is my green, the spectrum for my green color, okay, like this, okay. So here it is 2 5 by 2, and this one also, this point is 2 5 by 2, okay. So you can see that this pulse width is high, okay, pulse width is high for red signal, red pulse width is high, okay. So if you consider this point, okay, so you can see most of the signal energy will concentrate here, okay. So this we can say, no, other components are the amplitude is very low, okay. So most of the power will concentrate with this cycle, okay, okay. So you can see that for the high width power, okay, high width signal, so width is again, pulse width is high, pulse width is high, this this frequency range, this frequency range from here to here, okay, it is low, no, okay. But here the pulse width is low, pulse is low, pulse width is low, okay. But you can see the frequency difference here to here is high. Actually the pulse is decreased by 2 factor, and frequency is increasing by 2 factor, no, here the frequency is increased, okay. So you can see that, okay, to send this pulse, okay, so to send this pulse uh, with the considerable distortion, okay, at least we have this bandwidth, okay. For our transmission channel should have at least this bandwidth, okay, to send this pulse, this big pulse, okay. But to send this pulse, lower pulse, our channel should have this bandwidth. So we have more bandwidth, no? Okay. So what you get here, when the pulse width is decreasing, pulse width is decreasing, the bandwidth requirement is increasing. Okay. So what is pulse width discrete means? Okay. So you know that pulse width, if the pulse width is tau, okay, the pulse rate is 1 by tau, no? If the pulse width is tau, the pulse rate is 1 by tau. Okay. So you can see that if pulse rate is pulse width is high, pulse rate, that means data rate. Okay. Pulse is a data, no? One pulse represent one data, 0 or 1. Okay. So if you choose big pulse width, you will have low data rate. Okay. Okay. So if you guys have very low pulse width, pulse duration, you will have high data rate. Okay. So pulse width is low, bandwidth required is high. Pulse width is low means data rate is high. Okay. So you can see that for less pulse width, you will have high data rate, so bandwidth should be high. Okay. But very high pulse width, okay, data rate is low and bandwidth is also low. Okay. So did you get this point? It is very important. Okay. So this point is very important for baseband transmission, and also to understand that distortionless transmission, distorted transmission. Okay. So did you understand this? Okay. So if I tell it again, okay, that is why we get that is the things we understand with this spectrum. Okay. So we know that, again I will write. Okay. So pulse width low. Okay. That means data rate high. That means bandwidth required is high. Okay. Pulse width is low, like this pulse. Okay. So data rate is high. Bandwidth is also high. Okay. High. Okay. And for less pulse width. Okay. For very low pulse width, sorry, pulse width is low here. Okay. That means pulse width is low means this kind of pulse. Okay. This kind of pulse. Okay. So this width is very low. Okay. That means data rate is high, bandwidth is high, also high. And if we select the pulse width high, that means very high pulse width. Pulse width high means our data rate, the pulse duration is high, like this. Okay. Pulse duration is high, like this. This is the duration. So this duration is high. That means data rate is low and you should have low bandwidth. Okay. You should have low bandwidth. Okay. So did you get this? Actually, this is what we get from the spectrum of this pulse. Okay. Now, what is our problem? We have to evaluate the sinc function spectrum. Okay, sinc function spectrum. Okay, so I forgot to tell you this thing. Okay, so actually this part, this part, sine omega tau by omega tau. This part we represent as sync signal. So this is sync omega tau. Okay, sync omega tau. Okay, correct. So if we have, okay, so if we have any time domain signal with a rectangle t by 2 tau, okay, 2 tau, okay, I will put here tau, okay, that means our pulse width is tau, not 2 tau, okay, that means it is just like pulse is like this, minus tau by 2 to, okay, plus tau by 2, okay, minus tau by 2 to plus tau by 2. So a rect t by tau, okay, I will write this with the t tau, okay, otherwise you will get confused. T by 2 tau, we get our spectrum x omega, okay, x omega as 2a tau, 2a tau sine omega tau by omega tau, isn't it? You get this? I'll check it again. Okay, no, 2a tau sine omega tau by omega tau. Okay, so if we get the Fourier transform of this xt, okay, we will have the Fourier spectrum as 2a tau sine omega tau by omega tau. So we can say this as this, instead of sine omega tau by omega tau, we can say sync omega tau. Okay, correct. Okay, so we have this Fourier transform pair. Okay, and also if you get the inverse Fourier transform of this 2a tau sine sync omega tau, you will get this rectangle pulse again. Okay, so this is one Fourier transform pair. Okay, okay, and you can see that if the rectangular pulse is a rect t by tau, that means minus tau by 2 to plus tau by 2, okay, then you will have 2a, here it is 2 tau, now it is tau, so tau by 2, okay, here because this is tau, so it should be tau by 2 sine sync omega tau here, when it is 2 tau, here tau, okay, so here it will be tau by 2, correct. So we will have this identity also. Okay, so if the rectangular pulse is a rect t by tau, we have this 2 and 2 cancel out, phi tau sync phi omega tau by 2. Okay, so this is, I think you better, if you can keep remember this, it is better. Okay, so this is very important result in communication system. Okay, in communication. Okay, so actually now our target is to find the sync function spectrum. Okay, so sync function spectrum we have to find. Okay, so how can we find it? Okay, say we have xt signal, time domain signal, it is a sync signal. Okay, so you have xt signal, it is a sync signal. Let's say it is a sync omega naught t, this kind of here it is sync. Okay, so we want to find the spectrum of this sync function. Okay, so if you tired, let's have 5 minutes break and then we start. Okay, so I hope you have time, because I can only continue this up to 5 o'clock. Okay. So we will try to evaluate the sync square function also. So just have a 5 minutes break. Otherwise, it is very boring. No? So